Good morning, everyone. My name is Yue Fan. I'm a Senior Development Engineer at UCLA NanoLab. In today's presentation, I will introduce you to the electron beam lithography capability at NanoLab. Here is an outline of today's presentation. I will start with the e-beam lithography system overview. So first is kind of what is the e-beam lithography. I know most of you has nano of microfabrication background. You are familiar with this, but this slide mostly for who might be kind of new to clean room. So e-beam is just we use a focal beam or electrons to create patterns in the surface. So we have a substrate here, and we have the electron beam sensitive resist. So next step is that we shine in the beams. So the beams comes here. As you see that, the beams has to go through each pattern. It's not like ones. So it's kind of like this one by one. If you have small pattern here, for example, it's right here, and then right at the parts. So for that reason, the speed is an easy work. I also write it here. It's not. So after developed, depending on the resist, if the positive resist, you will get structure like the left side one, and if the negative resist, you get right side one. That's basically for the lithography system. If the optical one is use optical, is use a light to shine, and for the e-beam we use electron sensitive beam resist. So by now you will see that most of the advantage of the e-beam is the resolution, because the beam can be focused very well, so that you will see the resolution can be very high. The beams for our e-beam writer inside clean room can be focused to the spot size about less than 5 nanometer. So you can see that resolution can be really high. And placement accuracy is also an advantage of this, and also it's flexible because you can design any pattern and just use CAD and then you write it. The disadvantage, obvious, is kind of the speed here. Okay. So the next one, it's also kind of basic idea. People might ask what kind of tool they can use. So here I just give a brief guideline of what we can do with the different tools inside clean room. Sure, for the details of each tool, please contact the corresponding staff members. They will introduce you more details. But here, just give you a brief guidelines here. So, you know, we have the Kaosu's master liner. That one, I would say about 2 or 3 microns and above. It's lower than that, people want to use a stepper. We have the SM stepper here. And that one is about 300. And less than that, you will have to use e-beam. So for our tool inside clean room, so its resolution is sub 10. I give this arrow here, that means really it didn't mean it cannot write big pattern. You can go even higher one, just but for the e-beam and the writing time might be another issue. Okay, so here is the main thing here today. This race EBPG 5000 plus. Yes, you might notice VSTEC because when we purchase this tool, it's a VSTEC, so we are still getting used to that. But later the race purchased the e-beam tool, so now it's the race. Right. So from the tool, you can see that I just give you a brief idea of what's the tool. So the top side is the gun chamber. There's 3 or 4 ion pumps connect to it. It's reached the 10 to minus 9. So this is the main chamber, and there's airlock. We have airlock with 2 cassettes, which means we can load 2 holders at the same time. So these parts is the high voltage control parts. Mostly we run in a 100 kV. So here is a view inside clean room. When you step the e-beam room, you will see this one. Inside actually is a small chamber which mostly control the temperature. Usually we use 20 degrees. It's really goes through the 3 digits after that. This is the control side with outside this room. The table is here. And here is a microscope. This is not kind of standard. It is stereo one, but it's not standard. It's mostly used for check the sample height. There is a laser to check the sample height, and also you can move around to get the coordinate. So the next, the key structures. So first, the gun source is the thermal field emission gun, and theoretically it can be handled at 20, 50, and 100 kilovolt. But mostly nowadays we just fix 100. 9 width, we get sub 10 nanometer resolution, which I will also show you some pictures later. And stitching and overlay accuracy use the industry standard. Mean plus 3 sigma is about 30 nanometer. And also we have the 2-position loading dock for batch process that's here. So that means we really can handle 2 different kind of holders once. And then after that, after loaded, the software can handle that. And we have different kind of holder I will quickly show you. So to hold the samples from piece to up to 6-inch wafer holder. And the standard operation beam current I write here is 130 picoampere to 100 nanoampere. Next one, here is the holder. You might be interested. So I think that's by now all the holders we have here. Here, this one is 4-inch wafer holder. This is 6-inch wafer holder, mostly very similar. So here, this plate, there's 2 different holders. The left side is 2-inch wafer holder. We can just mount a 2-inch wafer here. And right side is for the piece holder. We can mount different kind of piece here. So people might ask what size you can handle with piece. As soon as it can stand here, we can use these screws to fix it. It will work. For the height, really, I think a few millimeter, even we can handle. So definitely if you have some spatial samples, we can talk, we can run a test. This one is 5-inch mask holder. We really can also write some 5-inch mask here. Okay, so the software system. Okay, so the tools base is the operating system is Linux, but the company is very good at develop the GUI system. The company developed like C job. I just give you an example here. So this C job is just like Windows, Word, or PowerPoint. For example, you just drag or design in a CAD file. Just drag and drop, and you can design. So left side one is just a simple one. We have 2 layers, so we have the flow to write 2 different patterns with different beam current, for example. That shows that because the green one, the bigger one, is covered red one, so you cannot see the red one by now. The right side one is a little bit complicated. You can see that you can, based on this one, the left side one, you really can drag and drop, write the most complicated structure. So the C-View is the tool built-in program which you can check the pattern. For example, for the blue pattern, if you right-click it, you can just use C-View to view this. You can zoom in, what's inside, you can mirror it. So it's a very powerful tool to quickly check the pattern and do some measurement. So next one we'll talk is about the Genesis beamer for pattern fracture. This is the kind of bridge to build a bridge between the pattern, user design pattern to the machine readable one. So we accept, mostly we recommend the GDS format, but we do have a lot of DXF or CIF. It's mostly GDS and DXF. So we can load to this software, which is just use a different strategy to convert the patterns to the machine readable. The format is called GPF, Generic Pattern Format. So the company for this software is Genesis Beamer. For the Beamer, there's you can see that there's so many different functions here. For general users, I don't think they will use a lot of them, but that means it's here. If you really have some complicated design or complicated things you want to try, you might want to play with it. But for the everyday running, I would say it's not so complicated. This is one of the simple example. You input the GDS file, and as I said, there's 2 layers, layer 1 and layer 2 here. Layer 2 is a bigger one, layer 1 is a small one, so you cannot see at this magnification. So if you zoom in, you will see the red one also. So we can just separate them to one is the left side one, one is the right one, and then we fracture at a different resolution. So based on that, we can write with the different beam. For the fine structure, we write small beam, and just for the bigger structure, we use a bigger current. So the next one, yeah, is just what I said, is you just go through this. And also, I will give you another thing the tool can do besides the beamer, is that the software itself has some basic functions, can add patterns like this one. So actually, this example for dose test is a 5x3 array of one dose test pattern, but we can write the dose numbers underneath easily. And this small size is also easy to add. You can add kind of square or just any shape. So by now, the process we have established, or we use a lot here. We have different kind of resist. We have positive tone. The resist, mostly we use either PMMA or ZAP. We offer PMMA 49584 and PMMA 950A2 in our clean room. That's free for the users, but you are welcome to bring any combination you want according to your needs. And for example, we have users use MMA, PMMA combination is also worked. For the negative tone resist, we have used is first is HSQ, officially it's also called XR1541. So it's a negative tone resist. It can reach very high resolution. We also have another series is the MAN 2400. Depends on the thickness of the resist. You can use MAN 2403. MAN 2405. Let's just give the different thickness at 3000 RPM for them. For the substrate, so for the substrate, we mostly we handle large. It's a silicon, and sometimes we have pores, or definitely we have 3.5. So for the next few slides, I'll quickly show what we have use this beam writer. So this is based on the HSQ. It's an image resolution. You can see that on the, here's just an example. We have the different spots on the sample. We all marriage and get continuously sub 10, 8 or 9 nanometer resolution. And here is what we just use the E-beam. At 1 nanoampere, we write the sample and then deposit tie gold on top. After that, you can see that the 30 nanometers resolution. So here is give you example alignment accuracy here. So this is the left side, this is which we write first on the with a tool, write it, and after that we write these 3 dots on that. If we zoom in, it's really about a few nanometers on each side. So you can see that that's accuracy here. Okay, so here is one example of it's a project we did here for one customer. So this is it's a golden nanobars on silicon. You can see that in the whole areas is kind of uniform, the whole areas. So the size what we achieve here is a 20 nanometer. I did run some tests at 12 nanometer. It's not as good as this one. For example, more you will see kind of like this areas at 12, but it's still we get I think over 50, but 50%. But here you can see at this resolution 20 nanometer, you can see the bigger areas. It's not only this one. If we switch to the other side, it's also kind of like this. It's really high resolution. It's not only the image resolution. It's after process. So you can see what the tool really can do that. Here is a customer project which user uses ZAP resist, write about 20 or 30 nanometer dots, then etch through that, and then they close a lot of wires on top of this courtesy of the Professor Hafika's group. So the next is how to submit the e-beam writing job. As I said, by now only staff member handling the tool. So you need to submit your request. As a new user, mostly standard is that they send us email or just go by the office and try to talk with us what they really need. And then it's better we schedule a meeting to ask what you really want. And if you really, depends on what you know about e-beam. Sometimes we talk about basic things, but sometimes it goes advanced things. It really depends. And after that, usually we we ask you, please fill, there's a form. I'll show you later what's that form. That's kind of standard form for each e-beam request submit, and you have to give that form. And also, users have to go back to prepare their patterns. As I said, the GDS, DXF, or any other format, we recommend GDS or DXF, but other format definitely is acceptable. So after that, we can make a reservation. Before you schedule time, you need to code yourself who is the resist. I can help you if you cannot access clean room, but if not, if you can access screen, definitely it's better you did that by yourself. Okay. Later is e-beam writing. After that, the develop work is also the same. You can develop it by yourself if you are a user here, or we can develop for you. Okay. So here is the e-beam job submission form. As I said, you need to submit this form for each writing. So basically, with this form submitted, I can use it to write your sample. So the next one, yeah, I will talk a little bit about alignment marker. That might be some basic things. So first, the marker type. The marker can be the rectangle across. For example, the simplest one is square, like 20 micron square. The size, it can be 10 to 100. It cannot be too big. Okay, so maximum is 100. And marker, to marker distance. Okay, that's also one things, kind of important things is we said if you have two markers here, it has to be at least 2 to 3 times marker size. Okay, another things people think about more is about the writing time. That's almost the basic questions I get each time when user, especially new user come, or even repeat user said, hey, I have something, how long is writing? So I give you here a basic guideline. You can estimate it a little bit, but sure it's not as simple as this one. As here you will see that is those times areas divided by current, right? In general, if you use this one, you can calculate it. But sure, if we need to consider the stage move time, stage stabilized time, pattern generator, stabilized time, kind of we call it all together settling time. So in general, is that I always ask user if you have the design, send to me, and I just according to the message you feedback to me, estimated writing time. I mean, actually what I do is the fracture the pattern node to the tool and give you roughly the estimation time here. Okay, so by now I've talked about the RACE eBPG 500 plus ES system. So the next I will spend some time to quickly talk about another SCM based lithography system. It's located in CNSI B level, room B102. It's as you see here, the next slide one is just a standard SCM from JEOL, and it's combined with MPGS software. MPGS is a nanometer pattern generation system software. This tool can be only used as the SCM or combined with both. So when we train the user, we have different sessions. One session only for the SCM, another sessions is with added e-beam with the MPGS software function, and also we have another quantified sessions. So some highlights of this SCM. The filament is tungsten hairpin. Accelerating voltage is between 1 to 30 keV. And one thing I want to emphasize, you will see that bigger chamber. This one, if you open this door here, you see that it's whole thin. So your sample really can be very big. It says to be 200, that's 8-inch wafer. And the height is from here to here is 80 millimeter height. So if you really have some tall sample, which other SCM cannot handle, you might want to switch to this one. Okay, so talk a little bit about the nanometer pattern generation system, MPGS software. So this is the versatile and easy to use system. It can be added to any higher quantity of the SCM. And the software itself is very easy to handle. And they have their website as a JCNAPI. Okay, here just to give you example what this software can do. For example, we have a pattern file with two different layers. The left side one really bigger, and right side one, the smaller one, with another sense to just to view it quickly. That's the design. Okay, so their software is kind of that. You can add different entries here. So the first entry is just write this pattern once, and we have another entries array. Like here is we write 1 to 2 of these patterns, and we can separate what kind of each layer can do. Here like that. Layer 1, left side 1, layer 2, or layer 10 is right side 1. We can write it as different beam current or different dosage. So that's by now the basic of the things I would like to introduce today. And I would like to thank you for the staff members you see in NanoLab for their kind support. And also I really want to also thank you the Ray's company, their engineers, always for the more than 10 years support on this tool. Each time when we need help, they just can be reachable. That's also very appreciated. Genesis, this for the Beamer software, they are very active in these whole areas also. And always, if we have questions or users have questions, we can try to reach out to them and get help. And also, I would like to thank all the eBeam users to offer us opportunities to do the service for them and to develop their patterns, what they want. And also, thank you for your attention. So yeah, that's it for the talk today. So you are welcome to ask any questions. So next week, just switch to the Q&A. I'm happy to answer any questions you might have. And thank you for your attention again.
Can you go back to the page where you show us the example of the results, second example?
Okay, sure.
So what aspect ratio are we looking at for those nanopillars?
Nanopillars, really for these parts, is just not from my side. What we do is that we write these dots for them, and they develop it, and then use etching tool to etch and growth. I'm really not quite sure about the details, but definitely here is the person. Or you can go to their website to take a look.
Hi. For the stitching errors, do you have some common knowledge for how to avoid stitching errors?
Oh, the stitching errors, there's actually from two sides. One is from the tool size, right? Another is for the fracture size. So from the tool size, sure, like the drift might be most important here if you really consider or think about the stitching effect. So to minimize the drift, there's a lot of things to be considered. For example, the temperature mostly. That means if you really want to get or improve your stitching, you might have to wait a while. Just give you an example. You might have to wait a while after the sample loading to the inside the chamber before you start writing. That's definitely a tiny temperature shift really matters in that side view. Another thing for the stitching, I would say from the fracture side, right? You can use different ways. Mostly it's just one pass, but you can try the multi-pass. Beamer has these functions, can do that. That also can be improved, yeah.
What's the field size for you?
Field size, okay. So at 100 kV, which normally 100 wheel operation, so the field size is 256, yeah.
Micron or?
Oh, microns, 256 microns, yeah.
What's the resolution minimum size you can write?
Yeah, we set sub-10 mostly image resolution. That means we use HSQ, that's negative resist. You write it and see that, right? This one's 20. after all the process, we get the metal on top. I would say about 20. As I said, I did get about some bars about 12, but it's not as continuous as this one. I would say even it's still over 50%, but not like this. Like this, I would say over 90%. The whole surface is the same. Yeah.
For the marker, for the contrast marker, what's the marker depth you need for this alignment?
Yeah, that's a good question. I would say it depends on the materials, but I would say over 70 or 100 nanometers, or even thicker.
How many at least you needed for this marker?
If it depends on how accuracy. If it's just for the starting line, the basic line, if you just do the global alignment, you need 3 to define X and Y, right? But if you need hierarchy, sure, you need add local. So here, the example I show is here, like the green dots is for global, and the kind of orange dots is for the local.
For the local one, for each radical, do you need another alignment mark? Or at least for local one, do you need at
for
least
local
3?
One, example here, you just use these 4, but actually you can use like this one, and this one.
Okay, thank you so much. Thank you.
Yeah, you're welcome. I think we just can stop this webinar, and thank you again for your attention.